Hi everyone, and welcome to yet another video in thermochemistry, where we will talk about enthalpy changes associated with phase transitions, and I will also introduce the concept of enthalpy of formation. So here we go. So let's start with the phase transitions. What actually happens when water condenses? Well, a condensation process is a process where steam turns into water, liquid water. It's still water molecules, but it goes from a gaseous state to a liquid state. What actually happens is that the steam is cooled down until the condensation occurs. We can't have liquid water below 100 degrees, for example. We have to decrease the temperature, and then the steam will eventually be cooled down and condense. And why this happens is because the surroundings are cooler than the system itself. That means that energy will flow from the water molecules to their surroundings, because energy usually goes from, or always goes from, warm to cold. So energy is lost from the system to the surroundings as the condensation process occurs. So as the steam cools, the surroundings are heated up. That means that the enthalpy of the water will decrease, because energy within the water, in this case kinetic energy, will decrease, and therefore enthalpy, which is the concept of amount of energy, or like energy stored within the system, that will also decrease then. So we can make enthalpy diagrams for phase transitions. For example, a gas and a liquid. A gas is a system at higher temperature. The particles have higher kinetic energy. Therefore, their energy content, their enthalpy, will also be higher than, for example, liquid. Because enthalpy is energy content, right? That includes kinetic energy, so including temperature. When gas turns into liquid, it has to decrease in enthalpy. And what happens to this difference? Well, this energy is then given off to the surroundings from this system of, for example, water, during a condensation process. So when condensation occurs, energy is given off, and delta H has a negative sign because it travels from the system to the surroundings. If we have the opposite process, which is vaporization, then we need to add energy. We need to add energy to the energy content of the system. So that energy has to come from somewhere. So that energy comes from the surroundings into the system. That means that the enthalpy of the system increases, and we have a positive change. So we store enthalpy. All right. Let's also compare liquid and solid. Within a liquid, the particles move about. That means that they have a higher kinetic energy. Therefore, they have a higher energy content, that is enthalpy, than the solid does. The energy content, the enthalpy, also includes, for example, chemical energy within bonds. But we're not talking about that right now. Okay, so what happens here? Well, if we go from liquid to solid, that's a solidification process. Some also call this freezing. And in this process then, energy will be given off to the surroundings. And delta H will have a negative sign because the energy flows from the system to the surroundings. The opposite process is that of melting. In that process, energy is taken up by the system from the surroundings. We need to add energy to the system to make the particles move faster, have a higher kinetic energy. And that energy has to come from somewhere, so it will come from the surroundings then. It has to be added into the system by, for example, increasing the temperature of the surroundings. All right. So this is a way of thinking that allows you to think about what happens with both the system and the surroundings when we have a phase transition. Because Even though the delta H of the system is positive, that means that the delta H of the surroundings will be negative, right? Because the surroundings have to lose energy for the system to gain energy. So, enthalpy and temperature, they're not the same. One denotes energy content within a system. The other is a measure of kinetic energy of particles. So let's see. Let's look at a system where we slowly increase the temperature, and let's see how that relates to the enthalpy. So let's have temperature on the y-axis, and then we have the energy we add over time, the enthalpy, on the x-axis. In the beginning of a solid substance, let's think that we have an ice cube. We add energy to the system, we add enthalpy. That means that the temperature of that ice cube will increase, according to a linear relationship like this. Nothing very strange there. You heat something and the temperature increases, or you add energy to something and the temperature increases. Well, at the melting point, the temperature doesn't increase of the system until all of the substance has turned into a liquid state. So even though we add more energy here, the temperature does not increase. So think about an ice cube melting. The temperature of that system will be 0 degrees until all of the ice cube has melted. So why is this the case? Well, the added energy is taken up by the remaining solid substance and sort of used for the phase transition. At this point, any energy we add in will translate into giving the particles a higher kinetic energy. And until all of the particles are moving, we will have to continue to add energy because they equalize as the liquid part and the solid part are sort of exchanging energy between them. So the enthalpy will increase because we add energy, but the temperature will be unchanged until every single solid or every single particle in the solid state has been melted. So we can think of this that we go from different movement types. We go from only vibrations in the solid state to also translations, moving, and rotations of the particles as well. So that in order to cause these different types of movements, we need to add energy. We're also breaking bonds here. We'll get back to that a little bit more in detail. When we have a liquid substance, let's think water. It could also be anything. It could be iron. But let's think water. It's easier to visualize something we encounter often in the liquid state. Heating water in the liquid state will cause the temperature. Adding energy to water in the liquid state will cause the temperature to increase until we reach the boiling point. During the boiling point, the temperature will not increase until all of the substance has turned into the gaseous state. Why? Well, the energy within the system that we add, the extra added energy is used to overcome the chemical bonding, the intermolecular bonds. In this case, water, it's mainly hydrogen bonds in the liquid. So energy will be used both for that and it will be used for performing work against the air particles, right? They need to push the air particles away. Therefore, the energy will go to other things than increasing the temperature until all of the particles are in the gaseous state. Then the temperature will once again increase. So during phase transitions, the temperature is fixed at the melting point. If we're talking about water, the melting point of water is 0 degrees. And water will melt here and will not increase in temperature until all of the water has thawed or melted. We heat the liquid water, and then until all of the water has boiled off, that will only be 100 degrees. Until then we can add more energy and all of the gas has been then all of the gas can be heated and gain more and more temperature as we go. So, and we're gonna discuss this a little bit more. But we can also, there's many different types of concepts when it comes to enthalpy in thermochemistry. There's the enthalpy of fusion and the enthalpy of vaporization. And fusion is a different word for this phase transition melting here. So you can talk about enthalpy changes associated by various types of phase transitions. Here we have an example of water, where we have water going from the solid state to the liquid state. We've deduced that this requires that we need to add energy into the system, and it has been determined experimentally to be 6.0 kilojoules per mole. So this is standardized, so the more water we have, the more energy we need to add as well, of course. Vice versa, going from the liquid state to the solid state will then release energy to the surroundings by the same amount. We just changed the sign here. And we can also have enthalpy values associated with vaporization and condensation as well. In this case, the signs will also be reversed. Condensation releases energy to the surroundings. Vaporization requires energy to be taken up by the system, like so. These are values that you, of course, are not supposed to memorize or anything like that, but rather use and speculate around. They can be very useful when you're trying to figure out the enthalpy associated with chemical reaction. If you start with a solid that first needs to turn into a liquid before reacting, and so on. So, useful concepts, you don't need to memorize these values by heart. Okay, let's talk a little bit more about this. So, here we have different states of matter, and we've learned that there's different names for the phase transitions that we can have here, going from solid to liquid, that's called melting, liquid to solid solidification, going from liquid to gas is called vaporization, going from gas to liquid is condensation. We can also add sublimation when we go directly from solid to gas, and reverse sublimation, or in some cases called deposition as well. Goes in the other direction here. So here we have quite a couple of phase transitions. I've included all of them at the same page, or the same slide. And then the further up we are here in this picture, the higher the enthalpy will be. So gas will have a higher enthalpy than liquid than solid. Going from liquid to solid will then correspond to a decrease in enthalpy because we're going down in that direction. Going from solid to liquid, then we need to add enthalpy and add energy into the system. So we can sort of read it like this, related to this arrow here. Therefore, we know that sublimation results in an increased enthalpy. Okay. The opposite of this then is the strength of intermolecular bonding. We will have the strongest intermolecular bonding within a solid system compared to, and then sort of a medium strength, that will be a liquid system, and the weakest intermolecular bonding will be found in the gaseous state. And these two are then related to each other somehow. The enthalpy of the system is related to the strength of the intermolecular bonding within the system. Please note that I'm not talking about intramolecular bonding, I'm talking about the forces between particles, not within them. So, why are the intermolecular bonds stronger the lower the enthalpy is, and vice versa? Well, now we're talking about phase transitions. And we're only talking about physical changes, so I'd like you to remember that no chemical reactions will occur. That means that we will have no change in the electron structure, anything like that. What we are talking about is the relationship between the particles' kinetic energy and the intermolecular forces between them. So, and I've tried to add some animations here, so let's see how that works out in the end. Furthest to the left, we have particle arrangement in a solid. The particles are arranged in a neat, organized manner. They vibrate, but they don't move around. They don't switch places or anything like that. And that's because they have a low kinetic energy. They have low movement and energy associated with that. That also means that the particles will be very close to each other because they're not moving away from each other. And that means that we can sort of maximize the intermolecular forces we can have because they're very close to each other. If we look at the liquid state, and here you have an animation, and this will keep going, so I hope that this doesn't hurt your eyes too much. The particles will have, in this case then, a medium kinetic energy. It will be a higher kinetic energy than in the solid state, but a lower kinetic energy than in the gaseous state. The particles, they interact, they still have noticeable intermolecular forces here, but they're further away from each other because they have this movement. They have a rather decent amount of kinetic energy. So the distance between the particles will be greater than compared to a solid, and that means that we will have weaker intermolecular forces here because they can't get close enough to sort of maximize that interaction. When it comes to the gas, well, here we have a very high kinetic energy. That means that the particles will effectively fly away from each other. So they will move and be very far away from each other, and then they will have very weak intermolecular forces between them. Previously, when I talked about this, I've talked about that we don't have a difference in the intermolecular forces, but we notice a weaker difference. I'd like to correct myself on that account and say that we have stronger intermolecular forces in a solid than a liquid than in a gas, because of effectively the distance between the particles. So even though you have a master's degree in chemistry, you still learn as you go back to the basics. So that's a lovely part about learning. But yeah, so hopefully this sort of clears it out why we have stronger intermolecular bonds when we have a lower kinetic energy. And remember, this kinetic energy then will also be a part of that enthalpy because enthalpy is just energy content, right? So you looked at my lovely animations for far too long, and let's proceed. So we talked about physical changes here, phase transitions. Chemical reactions, though, they're chemical changes. So when we have physical changes, the intramolecular bonds are unchanged. However, we have a change in intermolecular bonds, as we talked. During chemical reactions, we see changes in intramolecular bonds, or the electron arrangement of the substances. That means we will have, when electrons move about and are changed about, that means we will have chemical reactions. So chemical changes are chemical reactions. And we're going to look at the enthalpy changes for a few chemical reactions as well. More specifically, those chemical reactions where compounds are formed from their corresponding elements. This is called enthalpy of formation. The change in enthalpy when 1 mole of a compound is formed from its corresponding atoms. The symbol for enthalpy of formation is delta HF, where the F stands for formation then. Again, this is a change in enthalpy. We don't have a fixed value before and afterwards, but we can determine a change. How much energy is released going from atoms to a compound, or how much energy has to be stored in order to force atoms to come together and form a compound. The unit for this is kilojoules per mole, because as you probably figured out, the more of the compound we make from the atoms, the more energy we need to add. So it's standardized versus the amount that is mole. So, an example of enthalpy of formation, that's when water is formed from hydrogen gas and oxygen gas, like this. Since we're talking about, here you have a chemical reaction, though normally when we write this, we would write the 2 in front of here, and have a 1 or nothing in front of this, and a 2 in front of the water. However, since this is standardized, we're talking about the enthalpy change associated with forming 1 mole of water. That's why we want to have the molar ratio for water, we want to have a 1 here, because it's a 1 mole of this. So then the rest will be standardized against that. And then we write half an oxygen molecule here. So this is the energy required to form 1 mole of water. And when that will be released in this case. Because you note here we have a negative sign of enthalpy. The enthalpy change is negative. That means that the products, they will be more stable than the reactants. A large negative value corresponds to a very stable product being formed compared to what you start with. Because a lot of energy is released, so you will have a lower enthalpy within the system. It's more stable. If we split water into hydrogen gas and oxygen gas, this would in turn require energy. And the delta HF, so the enthalpy of formation, would be 285.8 kilojoules per mole. This is the opposite sign, because it's the exact opposite process. If we break down water into hydrogen gas and oxygen gas, we flip that arrow's direction, and we change the sign, because that's going the other way, and that will correspond to a positive value. This chemical reaction is what unfortunately happened within the Hindenburg Zeppelin here, when it ignited and exploded like this on its maiden voyage. It was filled with hydrogen gas, because helium gas was very expensive at the time. And this hydrogen gas was supposed to be isolated from the air surrounding it, but for some reason it ignited, coming into contact with oxygen gas in the atmosphere, and a large explosion unfortunately happened. And a lot of energy was released. So, if the delta HF is a large positive value, that will mean that the substance has very unstable chemical bonds after the reaction has occurred. So now we're switching this around. In the previous example, we had a negative sign of delta HF. That meant energy being released, in that example, in the case of an explosion. Here we have a positive sign. That means that we have more energy stored within the system after the chemical reaction. So the enthalpy of formation for this compound here, that's a very large positive value. And when this breaks down, we flip the sign. If we change it around, then a lot of energy per mole would be released. That means that the products of that compound will be more stable. So if we break down that compound into its corresponding atoms, that will result in a more stable state for the atoms involved. Enthalpy, values of enthalpy of formation, they're found in tables, and they're definitely not something you need to memorize. But we can pick them out to find the enthalpy change associated with various types of reactions. And then, as you might learn later, we can take values for enthalpy of formation for different types of substances and sort of puzzle them together to form the chemical reaction we want. But that's something we will come back to in a future video. For now, I'd like to thank you for your attention. I hope you learned something today, and I will see you in a future video.